Hello guys, this is Paul McWhorter with TopTechBoy.com, and I am here today with lesson number 10 on using your Beaglebone Black Rev C microcontroller. This lesson is going to be bringing together a lot of the stuff that we've learned in the last few lessons, and what we're going to be doing is we will be creating a dimmable LED. You will need to hook up this circuit. You will need a potentiometer. You will need a LED. You will need a 330 ohm current limiting resistor, and you will need your Beaglebone Black. You will hook it up just the way that I have it here. I will step you through a couple of things. Top leg of the resistor we're going to be controlling from a PWM pin, and so we will be using pin 14 on header P9, and so we will be using header P9 pin 14. If we go back to yesterday's lesson, which was lesson number 9, we can see pin out that pin 14 is one of these purple pins. It's one of these pins that we can use for a PWM output. Also, in connecting up this potentiometer, we want to make sure that we reference 1.8 volts, and that is pin 32. If you run this up here at 3.3 volts or 5 volts, you will probably damage your Beaglebone Black. You want to make sure that the top leg of the potentiometer is hooked up to pin 39 on header P9. That is the pin that provides the 1.8 volt reference. As we've talked about in earlier lessons, when you're doing the analog reads, it only will read between 0 and 1.8 volts, and so you have to reference your voltage divider from 1.8 volts, which you get from pin 32. We will be using pin 34 as our ground, and we will be using our analog input pin 33. So from pin 33 here, it's an analog input pin, and we will be using that to monitor that center tap on the potentiometer. So let's go back to our lesson 10. Okay, right here. And so this was the pin 14. That is the PWM signal that is going to control the resistor. Goes to the long leg of the resistor, short leg of the resistor, goes to our ground rail. We establish the ground rail from pin 34. We establish the top leg of the potentiometer. Our reference voltage is pin 32, and then we are reading from the center of the potentiometer. We are reading the analog signal on pin 33. All of these on header P9. Hopefully that makes sense. Hopefully if you've been through the earlier lessons, you will understand the referencing scheme that we're doing, and it'll make sense to you what I am saying. Once you have this circuit hooked up, we have got to do a little math. The way this is going to work is you are going to read a value from this potentiometer. When we do analog reads, what values do we get back? We get a value between 0 and 1. All smooth values, analog fashion, between 0 and 1. If we're at 1.8 volts, we'll read a 1. If we're at 0, we'll read a 0. If we're at 0.9, we'll read a 0.5. So 0 to 1.8 volts, we read as a percentage 0 to 1. Okay, so what's going to be coming off of this center tap? 0 to 1. What do we want to apply on the PWM, on the LED? Well, we do this with PWM, and the parameter that we apply to the PWM pin is duty cycle. A duty cycle of 0 means that it's on 0% of the time. That means that it's flat line, there's nothing happening. So a PWM duty cycle of 0 means it's always off. A PWM duty cycle of 100 means 100%. That means it's always on. A duty cycle of 50 means that it's on half the time and off half the time, on half the time and off half the time, and so forth. And so what we have is that when we read 0 on the analog read, we want to apply 0 because we want it off. When we read 1, we want it to be full bright, so we want it to apply 100. And then we want to scale things between 0 and 100, when we read from 0 to 1. Okay, so we have the input 0 to 1. We want to apply an output 0 to 100. Normally, what you would think about doing with something like that is drawing those 2 points, a straight line between the 2 points, and then come up with a linear equation. The problem is the eye. The way your eye perceives brightness is that if you just created a linear voltage on that LED, at the very low settings, you're going to be seeing lots of change, and then about a quarter of a turn, it's going to look like the LED is going to saturate, and then for the next 3/4 of the turn, you're not going to see any change in brightness. That's the way your eye perceives things. So what we want is something that we perceive a smooth and gradual, nice, smooth transition from all the way off to all the way on, and right when we get fully to the right, all the way on, it is just reaching full brightness. In order to do that, we cannot use a linear relationship between analog read and the PWM duty cycle. We need an exponential function. So we're going to have to do a little math here. Hopefully you'll follow along with me. Hopefully this isn't too terrible. If you don't understand it, just put the equation in like I have it, but hopefully you will understand it. First of all, we've got to come up with the 2 points, because if we're going to fit something, we're going to need 2 points. Well, if I read 0 here, I want it to be off. So what duty cycle would I want? 0. So if I have an analog read voltage, let me get this where you can see it. If I have an analog read of 0, what do I want to apply? I want to apply 0. Okay, I think I'm going to have to zoom this in a little bit for you to see it. So let me get this a little closer. Okay, so if I read 0, I want to apply 0. This is our first point. Okay, what do I also know? If I read at the other extreme a 1, I want it to be full on, so what would I apply? 100%. So the second point is going to be a read of 100 and a PWM applied of a read of 1 and a PWM applied of 100. So if I read 0, I apply 0. If I read 1, I apply 100. Now, this is the problem. I need an exponential relationship between those two. And also, at 0, I want 0. And normally, with an exponential, you never get to 0. And so we're going to have an offset in there. The way we could do this is we could say that duty cycle, this is what we're trying to calculate, duty cycle is going to be equal to some constant. We don't know what that constant is. We'll have to select that constant to fit these things. Some constant raised to the what? The analog read. Analog read. So we raise some constant to the analog read to get duty cycle. But remember, when we apply 0, or when we measure 0, we want to apply 0 so the LED will be off. We have to subtract some other constant, which we'll call B. So this will create a nice exponential between these 2 points. But we've got to go in and we've got to figure out what B and C is. Well, how do we figure out what B and C is? We put the points in and then we solve for them. The easiest point to put in is 0, 0. So we would come in and we would say duty cycle is equal to C to the analog read. Well, what is the analog value? It's the X value. So C to the 0 minus B. Okay, and then what duty cycle do we want when we apply 0? Well, we want 0. So when we apply 0, we want 0. So we want 0 is equal to C raised to the 0 minus B. Okay, now anything raised to the 0 is what? It's 1. So we have 0 is equal to 1 minus B. So B is equal to 1. All right, we have one of our constants. Now we put that in and we figure out the other constant. So we know that duty cycle is equal to C raised to the analog read. Okay, C raised to the analog read minus B, which is 1. Now, what is C? Well, I got to figure that out by putting my second point in. If I get an analog read of 1, I want a PWM of 100%, a duty cycle of 100%. So for that point, I want 100% when C raised to the what? What went with the 100? 1 did, so it's C raised to the 1 minus 1. Okay, now solve for C. Well, 100 is equal to, what's C to the 1? That's C, minus 1. So what is C equal to? C is equal to 101. So now I get my equation relating the duty cycle to the analog read. Duty cycle is equal to, what is C? 101 raised to what? The analog read minus 1. So duty cycle is equal to 101 raised to the analog read minus 1. Yes. And you know what's going to happen if you do that? You're going to find that math works, and you could spend the rest of your summer trying to do that by guessing and just getting something to work, and you would become quite frustrated. But in about 3 minutes, we were able to get it with math. Let's just go in and now look at what that curve looks like. I can go in and I can put this equation into Excel very easily. And when I put it into Excel, I get this. Okay? And look at it. When I apply, or when I read an analog read value of 0, what does it tell me that I should apply for duty cycle? It tells me 0. If I'd get an analog read of 1, what does it tell me the duty cycle I should apply? I should apply 100. If I get an analog read of 0.6, it looks like that I should apply a duty cycle of 18. And by getting this smooth exponential curve between 0, 0 and 1, 100, we will get something that will smoothly increase, and it won't have this problem of looking like it saturates. It's a problem when you're trying to do LEDs dimmable, and this will solve it most magnificently. Okay, we should be ready now to start developing some code. So let's get up our terminal window. Here is my terminal window. Let me go back to my root, to my home directory. So I'll say change directory and go home with the squiggly. If I look where I am in the root, the /root, because I am logged on as root. If I look what's there, ls, you can see that I have a folder called MyPython. That's where I put my Python files. If you don't have one, you can make one with mkdir MyPython like that. I already have one, so I won't put that command in, but I will change directory down into my Python. Why do I do that? Because then I don't have to keep putting the path names in. Okay, let's come up now with some code that will bring this circuit to life. How do we create and edit a file? We do nano. That is our editor. What do we want to call this? We'll call this pot LED. How about that? .py. Always put a .py on my Python programs. You don't have to, but it helps you keep things organized. It is a good programming practice. Okay, so what do we need to do to get this thing working? We've got to import our libraries. Import Adafruit, okay, BBIO. What do we want to import? We're going to do analog to digital conversions over here as we are reading pin 33. Okay, the potentiometer is going to be read. The center tap of the potentiometer is read on pin 33. And so what we are going to need to do is import our ADC libraries. So we will import Adafruit _ BBIO ADC as ADC. Okay. If you have the Debian Wheezy version 7, you will have this library already on your system, and it will load up nicely when you get this command. If you type this in exactly perfectly and you get an error, that means that you need to go update and upgrade your operating system so that you get the latest one, which should have this on it. Import. What else am I going to be doing? Well, over here on the LED, I am going to be applying to pin 14 a PWM signal. So I need to import the PWM capability. Adafruit _ BBIO PWM as PWM. What else? I am going to need some delays in here, so I need my sleep function. So I'm going to import, or I'll do it this way: from time import sleep. This will just let me use the simple sleep function when I need to. Let's set up our pins now. Our LED is connected to what? Well, we are on header 9, so we are pin P9 because we are on header 9. And then if you remember right, we connected to pin 14 as such, pin 14. Okay. We also have the pot, the potentiometer, and that center pin that we are going to be reading is on header P9, and we hook that up to pin 33. Okay. The other ones we don't have to set up because we're not reading or controlling. They're just ground and the 1.8 volts. I'll set it before and set it again. You can only set this voltage divider up to 1.8 volts. If you try to do more than that, you're going to ruin your Beaglebone Black. So don't get mad at me if that happens. I have warned you 10 times. Okay, we got to get our pins initiated. So we do a let's see, ADC for our analog to digital converter. We just say setup. We don't have to give that any pins. It'll set them all up if we just do ADC.setup. We need to start our PWM signal, so I'll say PWM.start. Okay, and then which is the PWM pin? It is the LED pin, which we set up here. Okay. What initial duty cycle do I want? Well, I want to start off with it off, so I'll put 0 duty cycle. And what frequency do we want to use? 1000 Hertz will work nicely. For PWM, for most applications, it doesn't matter what frequency you use, but 1000 works nicely. Now I'm going to be looping and constantly reading that LED. How do I loop forever? Well, I can do a while 1, because 1 is always 1. I put the colon indicating that I'm starting my while clause. Then, in Python, your while clause or your clauses are defined by indentation. Doesn't matter how far you indent, but just indent the same all the way through that same clause. What do I want to do now? I want to read where this potentiometer is. So how do I do a read? Well, I need a variable, my analog read. This is my variable. And what is that equal to? Well, I need to read that potentiometer pin. I do that with ADC, analog to digital converter, dot read. Okay. And then where am I reading? I'm reading the potentiometer, so it's the pot pin. Okay, I have read that. Now, I have to calculate the duty cycle. Remember the math that we went through? I have to calculate duty cycle based on that equation. Duty cycle is equal to 101 raised to the, how do I raise to the, in Python, it's star star, that's shift 8, star star. I raise it to the what? Analog read. Okay, and then I subtract 1. That's the equation that we came up with over here when we went through all the math. In fact, you see it here. Duty cycle is equal to 101 raised to the analog read minus 1. It is brilliant math. I love it when you actually apply math. Students, I teach math at school. Students always ask me, when am I ever going to use this? Well, this is a perfect case of how you need to be able to work with an exponential function. But I digress. Let's just print the duty cycle so we can make sure if we made a mistake that we can kind of see if it looks reasonable. Duty cycle. And then what we got to do is now we've got to apply. We calculated the duty cycle. Now we have to apply it to this this pin 14. So how do we do that? We do PWM dot set duty cycle. Where do we set it? Well, we want to set it to the LED pin, and then what do we set it to? Well, we just calculated it. Duty cycle. Duty cycle. All right. It's always good to put a little bit of a delay in here, so I'm going to do a sleep for 0.2 seconds. Just let it kind of run smoothly. That should be sleep 0.2, like that. Boom. Okay. What I am going to do now is I'm going to run this thing. So let's Control O, Enter, Control X. Okay, so what do we want to do? Python, I don't have to put a path name because I'm in the folder with this file, pot.led.py. And so let's see what happens here. Ooh. Line 13, sleep. Okay, I've got an error in there. Hopefully you guys caught me when I made that error. Okay, I think one thing I see here is I didn't close my parentheses there. I think that was probably it. So Control O, oops, Control O, Enter, Control X. Let's try it again. Okay, it is going there. Look at that. And remember how I wanted to go smoothly from all the way off to all the way on? I'm going to turn the lights out, and that way maybe we can see it better, okay? Hey, you can still see me. Okay, you can kind of see the LED down there. LED is right here, and we are all the way over on the potentiometer. You can see, let me turn it this way, okay. You can see that this is my duty cycle. My duty cycle is right at like 1% because I'm kind of like all the way over on the potentiometer. And when you're that low, then the LED itself is not on. I will begin to bring this up, and look at that, the LED, I can kind of make it go off, or just right when I start to turn it. Do you see it just barely coming on right when I start to turn it? I mean, I just got it where you can barely see it. Just barely see it. And you can barely see it when the potentiometer is all the way over to the edge. And now I'm going to start bringing it up. Oh, I'm sorry, I went the wrong way. Let's see. You can barely see it there. I'm just trying to see right when I'm turning it. I'm going to see. That is still on. I think that you can see. Let me see if I can make it a little darker there. You can see that that is barely on there. Okay, let's start bringing it up. Look at that. Bringing it on up, bringing it on up, bringing it on up. Do you see how you can very clearly see it continuing to get brighter and brighter and brighter and brighter? And right there, I'm at the full other extent. But you see it never saturated, it continued to move smoothly. So let me just go down a little bit. You see when I go down just ever so much, you're still perceiving changes in brightness. And so this is a most excellent dimmable LED. And I hope you understand how this math works. If you don't believe me, go back and do it the other way and just fit a line between those 2 points. And you'll see that that does not work nearly as well as this does. This could be one of the finest dimmable LEDs ever created. Paul McWhorter, TopTechBoy.com. If you like this, give us a thumbs up. Think about sharing the lesson. Leave some comments. Sometimes I wonder if I'm just sitting here talking to myself. Leave some comments. Let me know that you're out there. Paul McWhorter, TopTechBoy.com. We will talk to you guys later.